Okay, welcome in AP physicists. Today we'll be doing review on kinematics. Today we'll be doing review on kinematics. To start this off, I have a concept question, which is kinematic in nature. However, you definitely cannot use your current level of mathematics in order to answer it mathematically. So I have three different pathways to go from here, this top left corner, to down here, this bottom right corner. I have the black pathway, which is a perfectly straight flat ramp. I have a curved pathway B, which goes out at a higher angle than pathway A does. And then we get out here to some distance and then it drops. And then I have the reverse of that, C here, which drops first and then goes out to the destination. So in what order do y'all think these arrive at the final position, and why? Think about it and take a few minutes to think about it and then answer and try and write out a response that explains why using your physics vocab. And one other thing that's important, this is level, this bottom part right here, and this is on Earth, which means that the only thing driving the motion is, of course, the acceleration due to gravity. Did anybody do the Unit 2 progress check that I assigned yesterday? Anybody done that yet?
Not yet.
Not yet. No.
Okay.
Should we give her answer? Or not?
Yeah, 1 second.
Okay.
Okay. So let's go ahead and talk about the warm-up. A, B, or C?
Definitely A
I
first.
think it's A too.
Let's do this. On Zoom, there's an option where you can raise your hand. Do y'all see where that is?
Yep.
Okay. So if you think it's A, click raise your hand.
Mr. Rob, where's the raise your hands feature? I never see that. Oh, never mind. I found it.
Yeah, it should be on the, yep, right there. Okay. Okay, and then everybody lower your hands. Great. If you think it's B, raise your hand. Okay, lower your hands. And if it's C, raise your hand. Okay. Somebody who voted A, tell me why.
Isn't it because a straight line is like the shortest pathway to the next
Exploration
destination?
constant.
That is a correct description of geometry. The shortest distance between any 2 points is a straight line. So that tells us that pathway A is definitely the shortest pathway. Cedric, why option B?
I think it's B just because it's the most, like, there's no change over time. It's just a constant. So I feel like gravity would act on that more equally along the entire path.
It's important to keep in mind that gravity always points down, and that in terms of the direction that gravity will accelerate us, it's going to be G sine theta in the direction of the ramp.
Yeah. Sorry, I didn't realize B was the red one. I was okay. I thought it was A is the red one, B is the black one. I switched them up by accident.
So your vote is actually for A?
Yes, sorry.
Okay. Say 0. Somebody who voted for C, why defend C?
Okay, so
it was kind of counterintuitive.
it was like already like going a lot fast. Like it has a steeper ramp, so like I just thought it would get like more acceleration and it would already have a higher velocity.
That is the correct answer and the correct explanation. The answer is that pathway C is definitely fastest. Here's the deal. The acceleration in the direction of the ramp, the acceleration A, is always going to be equal to G sine theta, which is just a fancy way of saying the steeper the ramp, the greater the acceleration. And so here at this initial part for pathway B, this acceleration is going to be teeny tiny because the angle of the ramp is teeny tiny. And keep in mind that these vectors that I'm drawing, these are tiny accelerations, not velocities, right? And so it is going to speed up as it goes down the ramp, but the biggest acceleration that it will have is going to be here right at the end. And so while this last part here at the end will cause it to speed up, it went really slowly this whole time and then sped up at the end. In terms of A, it's going to have the same acceleration the whole time. So the whole time it goes down the ramp, it will have this nice constant acceleration. And for pathway A here, this is the only one that we could actually calculate the time for using regular old algebras. We could get the answer here. However, here's why C is our winner. At the beginning, the acceleration is huge, massive acceleration down the ramp. It gets a huge speed and then turns this corner. It speeds up early, and then it travels at that speed as it goes down this length of the ramp, even if the acceleration here is smaller. But since it picks up all of that speed at the start, C ends up being our winner. This is a really common concept question just because it's a little bit hard to think about, but effectively the answer is whichever one can speed up and get to a high speed first will be the fastest pathway to the bottom. However, I think it's interesting that this result is actually calculable from principle once you start doing a calculus. This was one of the first problems that was posed to Newton that he could not solve himself, Cole. It was solved out by one of his contemporaries, and then he was able to verify the solution. This is called the Crone problem, which is a thing worth studying in analytic mechanics. But effectively, the Crone experiment attempts to solve for what is the curve of fastest possible descent. And so let's take a look at this. So here we have a track that's set up with some different holders so that you could put different cuts of track into it. And you'll see that of the tracks that he has set up for it, that he's going to build into it, and some electronics to sense how quickly this stuff goes down. Yeah, just some like 3D printed junk. And anyway, at the top is a clamp that can hold 3 marbles in place simultaneously. And you'll notice that on the back side is a flat, just a straight up linear ramp. And then in the middle is the winning track. And then in front is the more extremely curved track. And the fastest curve of descent is always that middle one. The shape of that curve is called the Crone. It's some Latin that means least time. But so long as you travel down that Crone pathway, that is the fastest curve to reach that final destination possible. And it's mathematically definable if you set up your equations and then you minimize the time parameter using the properties of calculus. Is that stuff okay?
Yeah.
Yeah. Okay, so let's go ahead and start off with our quick, just real quick, dirty review of kinematics. What is it? How do we want to think about it? And how do we use our AP equation sheet to help us through questions like this? So keep in mind that kinematics means the mechanics of motion. So we know that we are doing some kind of kinematic equation, some kind of kinematic problem, if we are talking about motion and motion only. That is to say that this isn't the stuff that we do to figure out how to solve for forces. It's not the stuff that we do to talk about momentums or anything like that, because those other terms that I just mentioned, they involve mass, which kinematics does not involve mass. Now the one, not one, but here are some examples where we might have to do kinematics as part of some bigger problem, right? Let's say we were told about the motion of an object, and then we were asked about the force of the object. So something tells us about an object's motion. So we're given motion, whatever that motion is. And then we're asked about force. How should we organize our approach? What is actually being asked of us here? And this is a thing that we always kind of have to work backwards to. Whenever we talk about force and forces, what is the primary equation that we end up using?
F equals ma.
Yeah, Newton's second law, that's the big deal, that we live in a world where how hard you push something doesn't determine that object's velocity, it doesn't determine that object's position. we live in a world where for some reason, how hard you push or pull an object determines its acceleration, where that acceleration is scaled by the mass of the object. Now, which one of the terms in this equation is a kinematic term?
Acceleration.
Only the acceleration here is a kinematic term. Forces are mechanical terms, and masses are mechanical terms themselves. So what is actually being asked of us is to take our equations of motion, whatever they might be, and solve for A, whether or not it's delta V divided by delta T. That's one thing that acceleration is equal to. Or we could get wild and we could use the time-independent equation of motion in order to solve for our acceleration, which would be V squared minus V sub O squared divided by 2 delta X. This is also something that acceleration is equal to, just depending on what you are given initially. And so what this question is asking us to do is to use kinematics to get that acceleration, and then use that acceleration to get the force. Is this okay?
Yep.
Yeah.
Okay. If we are still doing kinematic questions the way that we were at the start of the year, then the way that we normally do that is by setting up a have-want chart the way that we did yesterday, and using that have and want chart in order to define which equation it is that we would like to use. Now, it is a tried and true method and it does work. However, I think we should be at the point to where we can simply think about what terms are missing, and then we can use that information in order to guide us to the correct equations. So here in this first one, V is equal to V sub O plus AT. What is this missing?
Delta.
Yeah, this has no data about position. So this has no delta X. What about the second equation? What's missing?
Final velocity.
Actually, so I guess that is true. It does lack final velocity, but you could reverse engineer it in order to use it to solve for final velocity. Yeah, I'll take that. No final velocity. So if you were looking to solve for final velocity, that middle equation wouldn't suit you. But typically we think of that middle equation as containing basically everything. And then what about that final equation? What is that lacking? This is the big one?
Time.
Yeah, there's no time there. That's our time-independent equation of motion. So if you're not given time and you're not asked about time, you're being asked to use that third equation. Other important things to keep in mind when it comes to doing a kinematics is that linear kinematics and rotational kinematics are identical in their approach. There's really only one thing which is actually different between the two sets of equations and the results that are produced by these two sets of equations and how you should think about them. Really, the only difference is the fact that we are swapping delta X, our change in position, which is measured in meters, for delta theta, which is the change in angular position of an object, which is measured in radians. But literally everything about solving one of these kinematic equations is the same as the other, with this one swap. So that is to say, let's say that a horse accelerates from 10 meters per second to 12 meters per second over a distance of 50 meters. What is that horse's acceleration, and how long did this take? And so this is the exact same problem in structure as the following question. A flywheel accelerates from 10 radians per second to 12 radians per second over an angular displacement of 50 radians What is the angular acceleration and how much time did it take? So these two questions are identical in terms of their solution, but what's different about them is the physical interpretation, the meaning of what these solutions are, but the math is literally identical. Also, fun fact, horses don't actually have 1 horsepower. Horses have actually like 1.2 to 1.5 horsepower, because horsepower is being measured as the average amount of work that a horse can do over the course of 1 hour. So when a horse sprints, it's actually doing more than 1 horsepower of work on average over that time interval. Nonetheless, let's go ahead and solve this one on the left, just to show that solving this one on the right, it's the same thing. So item number 1 here on the left, how do I solve for the acceleration? What's missing? What are we not being asked for initially? We're given a final, we're given a final and an initial velocity as well as displacement, and then we're asked for acceleration. But what's not being asked for initially is the time. So that means I want to use the time-independent equation of motion. So this is to say our final velocity squared is going to be equal to our initial velocity squared plus 2a delta x. I solve this guy for a. V squared minus v sub o squared divided by 2 delta x will give me a. And now the rest is plugging and chugging. So that's going to be 12 meters per second squared minus 10 meters per second squared divided by 2 times 50 meters. This is going to be equal to our acceleration. This is going to be 144 minus 100, which is 44. 44 then divided by 100 will give us 0.44 meters per second squared of acceleration. Is that first part okay?
Yeah.
And then for that second part, I want to know how much time did it take for the horse to cover this distance. So which kinematic equation should we use to solve for that time? Equation 1 or 2 or 3?
Can do 1.
Wait, to find time?
Yeah.
So 3,
No.
right?
No.
3 doesn't have time in it, so it's either 1 or 2. Solving 1 or 2 would both give us the same answer, except to solve out equation 2, you would be solving some sort of quadratic equation. You can get the correct answer by using equation 1, which will give it to us from a simple linear equation. V is equal to V sub O plus AT. We're solving for time here, so it'll be V minus V sub O divided by A is equal to T. And so it'll just be 12 meters per second minus 10 meters per second divided by 0.44 meters per second squared. And so whatever 2 divided by 0.44 is, will be the amount of time that it takes for the horse to speed up by this much. So that is to say that the horse covers that distance in 4.5 seconds.
Okay.
And again, this is nifty, but here's the mental picture that we want to have in our head. A horse was already going pretty fast, and then that horse accelerated, and at the end it was going faster. And all of these numbers comport so long as this is the acceleration, and this acceleration is also determinative of the amount of time that it took the horse to cover that 50-meter gap. Now, when it comes to how we deal with this question in terms of angular kinematics, rotational kinematics, it's exactly the same. Here's the only difference. We're going to use Greek letters. So this is to say that omega squared is equal to omega naught squared plus 2 alpha delta theta. So the angular speed of an object is equal to the angular speed of that object squared plus 2 times angular acceleration times angular displacement. Same equation. So solving for alpha here would give us the same solution that it does here. Omega squared minus omega naught squared divided by 2 delta theta will give us our alpha. And because I used the same numbers, the answers are going to be exactly the same. It's 12 radians per second squared minus 10 radians per second squared divided by 2 times 50 radians. And this will give us alpha, where alpha is equal to 0.44 radians per second squared. And that means solving for the time is also exactly the same. The only difference is the set of letters that we use. Omega is equal to omega naught plus alpha t. Omega minus omega naught divided by acceleration is equal to t. And again, this t will end up being 4.5 seconds. However, in your head, the mental picture that you want to have here for the flywheel is the idea that this wheel was spinning quickly at first, and then some kind of external force was applied on it. And when we apply a force on something that's rotational, we call that torque. Some sort of torque was applied on this flywheel in order to speed it up. And it took 4.5 seconds in order for it to speed up. So the math, the mechanics, identical. But what's different is the units and the interpretation. One describes a horse moving in a line. The other describes a wheel. Is this okay?
Yeah.
If I wanted to know the amount of force that the horse was putting out, what would I multiply this acceleration by?
Mass.
The mass would be one way that I could reverse engineer how much force that horse was applying. And then here, if I wanted to get the amount of torque that was being applied, what would I have to multiply this alpha by?
Force time.
Moment of inertia, right?
We would have to multiply it by the moment of inertia I, which is just the term that would tell us how difficult is it to rotate that flywheel. Okay, so in terms of the basics of kinematics, that's about it. In terms of what it will be that you'll be asked to do for any kinematics question, I highly doubt they'll be asking a straightforward kinematics question. But what is overwhelmingly likely is that they will ask a kinematics question as part of some larger question that you'll be asked about forces, where you must first calculate an acceleration to get that force, or you'll have a collision, and post-collision you'll have to calculate the motion of those objects. So know that no matter what, there will be a little bit of kinematics buried inside of one of the two free response questions that you guys will be dealing with next month. For right now, if you want to work on a thing, please go to College Board Classroom and check out the Unit 2 free response question. It's open and it's live, and I'm just going to leave it open and live until I get all of them in. And then once you submit your answers to that question, it'll show me the responses. I'll grade them and give feedback and then send them back to you through Classroom. And we'll discuss them tomorrow, because this is homework and it's due tonight.
Okay.
And you know, there's still another half hour left of class, so if you just want to do it now, I would recommend it. And if you have questions as you go along, you could just holler at me.
Mr. Rob,
Yep.
is it due tomorrow or today? Because on Classroom you have it due tomorrow at 10.
Oh, I'm sorry. It should be due today at 10.
Okay.
Oh, my brain is dumb. I was just thinking about what the deal was. I was like, I'm finishing way too early. Why is this? It's because I'm not done yet. I still need to talk about graphs of motion. Let me talk about that, and then you'll be free. Okay, yeah, that due date has been updated. Graphs of motion, that's the other big thing that always comes out of freaking kinematics. And since those of y'all in, a calculus are in a calculus, this stuff is a lot easier to think about. But let me just go ahead and give y'all a quick crash course on how we want to think about graphs of motion. Now, the nice thing about dealing with graphs of motion in terms of kinematics is that there's basically no area to consider. When it comes to other types of graphs of motion, like force versus position or force versus time, the areas underneath those types of graphs, they interest us. And that's mostly due to the fact that if you have force graphed over position, if you were to take the area underneath that graph, that would actually tell you how much work is being done. Don't worry about getting that into your head right now. We will come back to that when we do our review day on energies. However, when it comes to graphs of motion for kinematics, here's what you want to look for. We want to be able to take and we want to be able to interpret different graphs of motion and relate them to one another. And so here's how I'm going to break this down. If you are in a calculus, please consider the following. I have my position, which is a function of time. I have velocity, which is a function of time, which is equal to the position's first derivative. And I have acceleration, which is a function of time, which is equal to the velocity's first derivative, which is equal to the position's second derivative. Yeah, and when y'all learn basic calculus, what is our, how do we want to conceptualize taking a derivative? When you take a derivative, what is that calculating for?
The slope.
The slope of a tangent line of that graph. This is the exact same thing as saying that velocity is the slope of position. And this is to say that acceleration, what?
Is slope of velocity.
This is the slope of velocity. And if you think about slope, like what that is, this makes good sense because m is equal to the change in y divided by the change in x. So what this derivative idea is talking about is that, well, the velocity is the slope. If I were to graph position versus time, and consider how that graph is evolving as we move into the future. And so here are some different ways in which this might come up, in different ways in which you might be asked to relate some different graphs of motion. Keep in mind that velocity is the slope of position and acceleration is the slope of velocity. So let's go ahead and say that I have the following graph of acceleration. And this acceleration is changing over time. It's not like our normal accelerations like gravity, where gravity is just a constant and it always points the same direction. I'm going to go ahead and say that at some different times, my acceleration is going to change. So here at the beginning, my acceleration is this. And then in the middle, my acceleration is this. And then down here at the bottom, my acceleration is this. Where we start off at time is equal to 0, and then we hit some time 1, and then we hit some time 2. And this is acceleration versus time. Is this okay?
Yep.
Yeah, okay. So, believe it or not, this is enough information to produce the graphs of velocity and the graphs of position. Let's go ahead and start off by graphing our velocity function. And to do that, I'm going to go ahead and I'm going to replicate the exact same time intervals. So we want to figure out what is the graph of velocity versus time. And all that's important is that I have the same time interval sets. So time 1, time 2. What should my graph of velocity look like then?
Should it be like a positive slope for like the first box, like the first time interval?
That is perfect, yes. So keep in mind that when thinking about these graphs, because of these derivative relationships, acceleration is literally the slope of the velocity graph. So let's go ahead and read the function values for acceleration. In this first interval, it's some positive number. So that means that the slope needs to be some positive constant number. In the middle, what is the acceleration value?
Is 0.
In the middle, it's 0, which means that in the middle, the slope of the velocity needs to be 0. And then here at the end, the acceleration is
Negative.
negative. And whatever this number is, its absolute value is smaller than this number, just because it's a little bit closer to the axis. So here's what I know about our velocity graph. In the first interval, the slope needs to be positive and constant. So if an object has a positive acceleration, its velocity is going to gradually increase. That seems to make good sense. Is that okay?
Yep.
What does it look like in that middle region, the middle interval?
It's just straight.
Horizontal line.
It would have to be a flat line. The acceleration is 0. We're not speeding up, we're not slowing down, and as a result, the velocity becomes constant. And then here, the acceleration is negative. So what happens to our velocity?
It's a negative slope.
We will, yeah?
Yeah, and then does it go under 0?
It does not, because this acceleration is smaller than this acceleration. So
Oh.
here, this is almost a slope of 2. To make sure that this is an appropriately scaled graph, here to the right, the decrease in velocity would have to be more gradual than the increase was over here.
Okay.
Big acceleration, big slope, small acceleration, small slope.
Okay.
So this would be a really good approximation of what the velocity graph would look like here for the acceleration. Now, the only thing that could affect this is this acceleration didn't give us any information about what the initial velocity was. This graph right here is kind of making the assumption that we are starting from rest, which itself is a dangerous assumption. Now, that's not that big of a deal, because if we had some initial velocity, what would it affect about this graph?
Starting
It
point.
starts.
Literally, yes, it would only affect that starting position. So the picture would be exactly the same, but if we were starting off at some positive velocity, then it would be shifted up. If we were starting at some negative velocity, it would be shifted down. All you have to do to fix that, if you did this wrong or you didn't notice that we had some initial velocity, is change the definition of this axis from 0 to whatever number the initial velocity was. If we were told that v sub o was 15 meters per second, then this graph is still correct as long as this is 15 meters per second on the axis. Is that okay?
Yep.
Yeah.
Great. Okay. And now finally, the position graph. So what does the position graph look like for an object which initially speeds up, then turns on cruise control and continues to move at a constant velocity, and then it begins to slow down? What does that position graph look like?
Like,
Is it exponential at first?
it just
Be
like
very careful with that word. It is curved at the start, but not an exponential curve.
like a hill, up and down.
So I'm going to add the same intervals because that's where our acceleration changes occur, t1 and t2. And this is position. So in order to help us think about this, keep in mind that the most valuable thing that Newton gave us, you know what, no, the most valuable thing that Newton gave us was actually Newton's laws. One of the most useful things in kinematics are the kinematic equations of motion. So here, right, we're trying to graph position versus time. What is the equation of position versus time? Which kinematic equation is that? 1, 2, or 3 as it's listed on your sheet there?
1.
That is velocity versus time. That has no positional information.
2, 2.
Equation 2. X is equal to x sub o plus v sub ot plus 1/2 at squared. So in this first interval, is there an acceleration? In this first interval, there is an acceleration. So in this first interval, since a is not equal to 0, what shape is this equation if you graph it? The part with a, what shape is this?
It's just a positive like curve.
What shape is the equation x squared?
Parabola.
A parabola. So if acceleration is not equal to 0, right, this equation is going to have one of two shapes depending on these terms. If a is not equal to 0, then that term survives and we get a quadratic. Yeah?
Mm-hmm.
So in this first interval, this object is going to move according to the 1/2 at squared part. So it is a curve at the beginning, but not an exponential curve, a quadratic curve. And even though it seems like those two things are similar, trust me, from a mathematical perspective, they are very different. We wish that the coronavirus outbreak was growing quadratically, but instead it's growing exponentially, which grows much faster as you move forward into time. Typically, quadratic graphs and exponential graphs will line up a little bit at the start if you look at them on a TI-84 graphing calculator, but as you go into the future, they diverge radically. In this second part, what do you think the equation looks like? So this is saying at the start, because we're accelerating, we're covering a huge distance very quickly. But then what? How much acceleration do we have in the middle region?
0.
None.
So if the acceleration is 0 here in this middle part, then this 1/2 at squared part, that whole thing gets zeroed out. So if a is equal to 0, what shape is that?
The line.
This is linear. So if a is equal to 0, then this becomes a linear graph of motion. And so we're still moving forward, right? So think of it like you're driving in a car. You get on the freeway and you floor it. Just because you take your foot off the gas pedal, just because you stop accelerating, does that mean you stop moving forward?
No.
No, you continue to roll forward, especially if you turn on the cruise control, because your car has the velocity that it did before you turned on the cruise control. So you keep moving forward, except now you are moving forward with a positive linear slope only. Yeah?
Mm-hmm.
Mm-hmm.
And then what do you think it looks like in this second part here?
That was a negative quadratic.
It is indeed now a negative quadratic. Now, again, you're on the freeway and you're driving, right? You take your foot off the gas. I'm sorry. You're driving on the freeway, you put your foot on the gas, and then you turn on cruise control. So now you are moving forward at constant velocity, and then you turn the cruise control off. What happens to your car?
It slowed down.
It begins slowing down, but does that mean that you start moving backwards?
No.
No.
No. You are still moving forwards, just not as fast as you were moving forward before. So in this region, we have a negative acceleration. So we will get a negative quadratic. So here we had positive quadratic. In the middle, we had positive linear. And here at the end, we are now going to get a negative quadratic, but we're still moving forward. So here's what it should look like. It'll be a negative quadratic, but it doesn't flatten out, because once we turn back, that means that, hey, we're starting to roll backwards now. So yeah, it is important to keep in mind that when it comes to graphs of motion, the velocity is the slope of the position, and the acceleration is the slope of the velocity. And as long as you obey these slope relationships, or when in doubt, you can fall back on the actual equations of motion to be like, oh, certain features are linear, certain features are quadratic to help you draw the curvy bits. That's all the information you need to read and interpret graphs of motion. Okay, yeah. Anyway, that's it for today's review. We have like another 10 minutes left, so if y'all want to work on that free response that I assigned, please do that. When we come in tomorrow, we'll continue on with our review. Tomorrow, I'm going to do a recap of projectile motion and how you want to think about it. And as I do these reviews, you'll notice that I'm going to reach forward to the topics that we covered since we learned the old stuff to try and draw some connections. We'll do the same thing tomorrow. We'll talk about projectile motion, but I'm also going to drag in some information from new sections for the sake of, making those connections between disparate sections.
Mr. Rob?
Yep.
For the free response, you want us to do where like each individual picture is just for that specific part, right?
Yes. Mhm.
Okay.
Yeah, and the big reason why I want y'all to do it that way, I think that's what the real AP test is going to be like. I don't know, but I figure the questions that they have set up are probably similar to the way the actual test will be formatted, so it probably would help to get used to it now. The other nice thing about taking these things from home, y'all, is that like during the AP test, you get provided a clean equation sheet the same way that you did every single time we took the test, you know? You're taking it at home. If you're gonna have access to all your notes. So if you make like little notes or manipulations on your AP equation sheet, or write in the margin some of the more useful pre-derived equations that we've talked about, like remember how we have the time of flight equation and the range equation and the height equation for projectile motion?
Yep.
Yeah.
I don't know, man. You can put those on there too and just have them ready to go in case they're useful.
Mr. Rob,
Yeah.
they wouldn't want us to like derive the equation, like show the work for deriving these equations on the AP test, would they?
No, that's exactly what they want. That's everything they want.
Oh, so that okay.
So, I mean, they're not expecting you to derive the equations that are on the AP sheet itself. They're expecting you to be able to use those equations in order to derive other useful relationships. Like how if you took the force due to gravity and you set that equal to mv squared over r, right? If you said gravity is the centripetal force driving the motion of this planet, if you set that up and do the math right, you can use that to calculate the length of a year on Earth. They are expecting you to do algebraic manipulations. That is what actually gets the points, not the answers. No one cares about the answers.
All right.
Mr. Rob,
Yep.
when we have two blocks and one block is heavier than the other while the other one is hanging, it doesn't matter of the weight, right? Since the smaller block is always going to pull the heavier block down if it's on the pulley system.
You know, I guess that's kind of the point of that question. I want you to deal with it. I would consider, so the big idea to that question is everything is at rest, right?
Yeah.
So if everything is at rest, not only is the velocity zero, but what else is zero?
Acceleration.
Yeah, and if the acceleration is zero, that means the sum of all of the forces is
Zero.
also zero. So for every single object in that system individually, you should be able to name the forces, like there's the weight due to gravity, there's the normal force, and there's the tension. But you should be able to reason out what the relative magnitudes have to be, because you know that in the end they all add up to zero.
Okay, but do we have to include block 1 too? That's why I kind of got confused. I don't know if I should take into account block 1 is holding up block 2 or not.
It contributes a force if they're in contact. It's contributing a normal force. And it's important to draw the free body diagram for each one of those objects independently.
Okay.
Give it your best shot, and then tomorrow when we start up lecture, that's the first thing we're going to do. We'll go over that free response together.
Mr. Rob,
Yep.
for the Unit 2 FRQ that's on AP Classroom, do we have to print it out and then take a picture and upload it?
No, dog, no. Just do the work directly into College Board Classroom on there. I can actually see your responses after you submit them.
Okay, because I don't know how to like draw on it or use Word or PowerPoint or something to be able to draw the free body diagram.
Oh, I mean, you could just do it on paper and then take a picture and then upload the picture as a JPEG.
Okay.
And I think this is probably how the test is going to be, that they'll expect you to do a little bit of free response work and then just take a picture and upload it.
Okay, thank you.
Mm-hmm.
Mr. Robinson,
Yeet.
all the do nows and all of these lectures are on YouTube, correct?
Yeah, so if you ever are busy or have a work shift or whatever during the class, just check it out. And then if you do watch the video on YouTube, shoot me an email and I'll fix the attendance for that day.
Yeah, I usually like your class does happen during my work shift, so I just kind of have one AirPod on your class while I'm assisting customers. I'm just on mute. So I don't really have time to do the do nows except until after work. So I'm just asking to see
Yeah,
if I'm
yeah,
still.
that's fine. I ain't hating. That's my life too, dog. Like when I'm watching my like boring evening grad classes, if it gets really boring, I just like leave my headphones on, listen to the lecture. If he asks a question, I pay attention. But like right here is my gaming computer. So if I said I was never on my other computer while I was supposed to be paying attention to class, I'd be a liar. That's all fine. Just like learn to manage your time.
Yeah, I am. Thanks,
Tight.
Mr. Robinson.
You
I'm gonna go. Bye.
peace. The rest of y'all feel free to roll. Oh, actually, yeah, class is over. I hope that review was something. Y'all have a nice day. Do that free response. We'll go over it tomorrow. Tomorrow we'll roll into review on a different topic. You'll get another free response to do tomorrow night, and we're just going to keep crunching away at it until we're all in a good place.
Thank you.
Y'all have a nice day, and I'll see you tomorrow.
Bye.
Bye.